Relatively Prime was made possible by the 159 people who were kind enough to give it money on Kickstarter. Now, while I would like to thank every single one of them by name, we do have a show to listen to here, so instead I'm just going to thank Jared Musto and Chris Schneider, as well as my Kickstarter producers, Martin Dominic, Edmund Harris, Cody Palmer, Jay Frosting, Colin Wright, Douglas Dollar Stewart, and Daniel Greenspun. Thank you all so very much, because without you, Relatively Prime just never would have happened.
The reason that I got interested in this is that after having written a book on maths, I would go and give talks. I would sort of meet people, and they'd be like, "Hey, you the math guy?" And I'm like, "Yeah." And he goes, "Hey, so what's your favorite number?" And I thought that was like a heckle, an annoying heckle. People just trying to sort of tease me or demean me, and I was thinking, no, favorite numbers, that's ridiculous. It detracts from the seriousness of the maths, which is what I'm here to talk about. But so many people asked me, and when I started to ask around, even some of my friends, I'm like, well, do you have a favorite number? They're like, oh yeah, it's 13. Oh yeah, always loved 8. I thought, this is weird. So like people do have favorite numbers, because I myself don't have a favorite number. I think that's kind of crazy. But the more I asked, not only did I realize that most people who I asked seemed to have a favorite number, no one thought it was a ridiculous question. And they seemed to have their beliefs that they loved these numbers, that they were favorite, really quite strongly.
That was Alex Bellos, author of Here's Looking at Euclid, or Alex's Adventures in Numberland if you happen to be shopping in the UK. And we'll hear more from him later. Today's show is all about the forgotten mathematical tool of numbers. Okay, forgotten may be a bit strong, but after a certain point in mathematics, numbers seem to lose a bit of their importance. For the first few years after you start to learn math, it's all add these numbers, divide these numbers, or find that number. And then it morphs into for all numbers, or let x be an arbitrary number, or for epsilon greater than 0. And numbers start to lose their power. Well, not today. Today, we'll hear about amazing properties of numbers, how a person started collecting collections of numbers, how research can lead to a number horde which can then lead to more research, and of course, all about favorite numbers. I am Samuel Hansen, and you are listening to Relatively Prime. Stories from the mathematical domain. Have you ever wondered whether a certain number was hungry or happy? Evil or aspiring? A Catalan or a Smith? Well, thanks to Number Gossip, a wonderful website created by Tanya Kovanova, a freelance mathematician working as a research affiliate at MIT. You can now check. She was nice enough to invite me into her home to talk about the project. And so, without further ado, here is Tanya Kovanova. Actually, there is a little bit more further ado. I should let you know that the other voices you hear in this interview are her son and collaborator on the website, Alexei Radul, currently a visiting scientist at MIT, and his son, Lev. So I'm here to talk to you about Relatively Prime. Relatively Prime is my show. I'm here to talk to you for Relatively Prime. I'm here to talk to you about Number Gossip, which is a website that you have. So I was wondering if you could just explain to my listeners a little bit about what Number Gossip actually is.
Number Gossip is a website where you can put in your favorite number, and it will tell you many properties about this number. It can tell you if it's prime or composite, whether it's perfect, abundant, or deficient. It could be evil or odious. It could be many other things. It could be a vampire number. It could be a weird number. It could be, many more. In addition to that, I collect unique properties of numbers. I think it started with the way mathematicians congratulate each other on birthdays. Like someone congratulated a friend of mine when she became 28 as becoming perfect. 28 is a perfect number. But after 28, she stopped being perfect and she became prime because 29 is a prime number. And the next, at 30, you are round, and 31, you are prime again. So it's sort of, the vision was to give people other things to say about a number when they congratulate their friends on birthdays.
As of right now,
That's why it goes up to 10,000.
Yes, that's why it goes up to 10,000. So when I started Number Gossip, the first thing was I collected some famous properties like prime numbers, Fibonacci numbers. And then I decided, other than famous properties, I want to collect funny properties like lazy caterers numbers or cake numbers. So there was a mixture of important and funny, though lazy caterers numbers are important too. So initially it was just the list of properties, but later I saw other websites, and there was a website by Eric Friedman that is called "What's Special About This Number?" And there is a number, and it's the seventh Capricorn number, or it's the number 13 and the sequence of that. And I thought, why being seventh is so special? So I wanted unique properties. I wanted a number to be the only, or the smallest, or the largest, or never seventh. So I started collecting these properties, and I had a lot of fun with it.
So of the non-unique ones, and it's provided I count this right. You now have 49 properties that Number Gossip talks about. So you're one away from 50, which
I didn't know that. I didn't know that.
And who knows? I could open the computer. We could check to see whether 49 or 50 is actually a more interesting number by going to your site. So
49 is square, 50 is round.
How did you really find all of these different? I mean, there's one that's even, I believe, the Google number, which has something to do with an ad that they ran once. So how did you get all of these? I mean, 49 kind of shared properties, the non-unique ones.
So as I said, I picked up very important properties first, and then I Googled around to find a Google number. I found out what other people invented or worked with, and I just went for funny names.
Well, I didn't, honestly, before I found Number Gossip, I never knew that there was such a thing as an evil number. Or a lazy caterer number, which is perhaps my favorite title of any of them. I really happen to like that one.
Do you know what a lazy caterer number is?
I knew at one point.
So a lazy caterer number, imagine a pizza, and you want to cut the pizza with 3 straight cuts. And what's the largest number of pieces you can get with 3 straight cuts? And the number is 7. There is a cake number, which is almost the same as a lazy caterer number, but instead of a pizza, you have a cake. And if with 3 straight cuts, what's the largest numbers of pieces you can get? Then the question is, what's the difference between a cake and a pizza? All mathematicians believe that a pizza is flat. It's a 2-dimensional object. Well, technically, pizza is not a 2-dimensional object, but the idea is you're not allowed to cut pizza horizontally. It would be ridiculous to cut pizza horizontally, but you're allowed to cut a cake horizontally. And because of that, cake numbers are different from lazy caterers numbers. And in 3 cuts, you can actually cut into 8 pieces. You can cut a cake into 8 pieces.
Do you have any of these properties that you personally just really love? Any that are your favorite?
Yes, there are. I like evil and odious numbers. These numbers were invented by John Conway, and it's a pun on even and odd numbers. So evil numbers are numbers such that if you take a number and its binary expansion, the number ones in binary expansion is even. So it's easy to remember: evil, even; odious, odd. And then after he invented them, they started appearing in many places. I don't have my favorites. They change from time to time.
So what sort of criteria do you use for deciding whether or not, say, a property is actually, interesting enough or important enough to go in? Because I'm pretty sure that I could just arbitrarily define a bunch of properties and say, like, oh, look, all these numbers have this property, but it wouldn't necessarily be one of the famous ones, wouldn't necessarily have any meaning. So what sort of properties do you look for?
So I don't know why, like parameters, I don't know why, like when it says it's the third number that blah. So I like to avoid that. So it should be the only, the smallest, the largest, or something like that. On the other hand, smaller numbers have tons of interesting properties, but larger numbers do not. So for larger numbers, I'm less strict than for smaller numbers. And also, many people sent me, that the number of Harry Potter's world was such. I'm trying to avoid non-mathematical properties. I actually have a couple, but at some point I decided no more. And I think I have something like I couldn't resist. 9 is the number of people in the Fellowship of the Ring, things like that. A couple of things, but mostly this should be mathematical properties. So, can you tell me what are abundant numbers and deficient numbers are?
No.
So perfect numbers sum up to themselves. Abundant numbers sum up to a number that are larger than the number itself. And deficient numbers sum up to numbers that are less than itself. So I have this sort of complementary properties. So on my website, every number has several properties. So, for example, numbers larger than 1, they're either prime or composite. Every number is either even or odd. Every number is either evil or odious. And also, again, all numbers larger than 1 are either perfect, abundant, or deficient. So at least 4 properties are there for every number.
I was wondering, when, I'm trying to figure out the proper way to word this. What sort of actual interesting mathematics might people come to just from kind of starting to look at interesting properties that numbers might have in relation to each other? Like, is there? Because I mean, a lot of people would just think, oh, this is a Q thing. Look at these properties. I was wondering if you might be able to take, kind of these. Oh, this is a sort of interesting thing, and if you know of any examples where you can actually then spin it into an actual kind of research.
Oh, of course you can spin an actual kind of research. For example, if you decide that you want to find a number which is a cube and a sum of 2 other cubes, and you're on the way to prove the last Fermat's theorem. I mean, there is a lot of modern research is hidden in properties of numbers. Some of it called number theory, but I think it's bigger than that.
I come to that because one thing that mathematicians tend to say quite often is that mathematics isn't numbers. I mean that mathematics is so much more. It's so much broader and such a bigger thing that I think that we may have even kind of gotten to the point where the idea of actually looking directly at numbers is a little bit kind of pushed to the side. And so I like the idea that there are actually things that we can directly look at numbers and find things that turn out to be important mathematically.
Yes, of course. Yes, of course. I think there are many things like that. I think there is, in addition to my number gossip, there is the website called the Online Encyclopedia of Integer Sequences, and there is a whole community that is working with sequences, and they're actually writing papers based on sequences. And my website is closely connected because very often if I have the smallest number that or the largest number that, it's of course there is a sequence with this all the numbers with this property. So I just I think the Encyclopedia of Sequences is huge, and the number gossip is sort of smaller. You have a couple of facts about every number.
Well, that'll actually help me time very well. I actually just talked to Neil Sloan.
So, this is what thousands of people see every day when
Do
they
you
come
actually get
across-
thousands of unique visitors every single day to it?
well, there are a lot of repeats
Oh, yeah,
over the period of a month.
Well,
But
yeah,
yes,
no, but I mean, like each day, like if you just take a day by itself, there you have
thousands, yes.
that is a lot of people looking at integer sequences.
And typically they've come across a sequence in their work or even on a quiz or something they're trying to identify. And there's only one place in the world you can go to try to understand what it is. At the simplest level, they're trying to figure out what the next term is, because that's what the quiz question said.
Yeah.
You know, here's a sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34. What's the next term? Well, if you can't figure it out, you look it up. Here, you type it in, and you click search, like that. And so it's called the OEIS, which stands for the Online Encyclopedia of Integer Sequences. But you can just Google OEIS, and it'll come right up. And when you click search, it tells you what it finds for your sequence. So here, for example, this is the number of ways you can draw a tree on n points. And it's sequence 55.
This is Neil Sloan, the creator of the Online Encyclopedia of Integer Sequences, available at oeis.org. I met up with Neil at the 2012 Joint Mathematics meetings in Boston, where he gave me a look behind the veil of the encyclopedia.
And when you get to it, in the OEIS, the entry tells you various things about the sequence. It'll show you the first few terms of the sequence. It'll tell you the name, the definition. In this case, it's a number of trees with n unlabeled nodes. And there'll be comments. One of the great things about this is that comments, they accrue over the years. People say, yes, but I have another way of looking at that sequence. And they add comments. These days it's a wiki. So if you're a registered person with the OEIS, you can add your comments to it. And of course they get refereed, they get inspected by the editors. So you get comments, you get to see references to the literature, and this is, in a way, the most important of all. This refers you to books and papers and websites that talk about the sequence. And then, very often, there'll be computer programs to produce the sequence for you. So here we have some Maple programs. There often are examples illustrating the sequence, little pictures, or more extensive pictures. Here we have, in this particular case, we have Mathematica programs. We have programs in Paris and in Magma, and there's a section linking it to other sequences, keywords, and the name of the person who sent it in. And as I said, it's a wiki these days, and I have a board of editors. It's controlled by a group of editors, and if you, I'm one of the editors-in-chief, obviously, and you can see the sequences, submissions by people waiting to be inspected. So, for instance, here's a sequence by Paul Hanna, who's been systematically computing sequences with a particular kind of generating function. It begins 11585, 2928, and so on. And so, he has a comment. It's surprising This is the kind of really interesting thing that we come across, that here he's observed something that is a surprise. It shouldn't have happened, that the exponents, the powers that appear in this formula are integers, and he doesn't know why. He says a proof is needed. It would be nice. So, all right, this looks like a pretty interesting sequence. I'm going to approve it. I click on this button here as an editor-in-chief. I can say I approve these changes, publish them in the OEIS. There it is. So we've added one more sequence to the database, and we're now up to 202,339 entries. We just passed 200,000 at the beginning of December. And how long has it been? What is it, the 7th of January today? So in about 5 weeks, we've added 2,300 new sequences. So I started this back in the middle 1960s when I was a grad student. I had a sequence I was trying to understand that had come up in the work on my thesis. And I couldn't figure out how fast the sequence grew. I really needed to know. And it would have been helpful if I had a formula for the sequence. And I looked in various books that had sequences in them, and I didn't find the sequence there. And so I started collecting sequences, because I knew I was going to have a lot of other sequences in my thesis that I needed to understand. And I thought it would be very useful. So I'm on little file cards. I started collecting sequences. And then once, well, it was hard to say no to a nice-looking sequence. So I accumulated, a few hundred. And then I put them on punch cards. It was easy to sort them and arrange them. That was around 1964 or 1965. And then the collection grew and grew and grew, and eventually I published a book with Academic Press in 1973 called A Handbook of Integer Sequences that had about 2,000 sequences in it. And it was a surprisingly good seller. And a lot of people bought it and said, gee, this is a great idea, and here's a sequence you don't have. So over the next few years, I got a lot of letters from people with sequences in them. And letters and postcards and off-prints of papers and preprints and handwritten letters from strange people and from prominent mathematicians and from non-mathematicians. And so my collection of material grew and grew and grew, and eventually in 1995, with the help of Simon Plouffe, a mathematician from Montreal, we published the Encyclopedia of Integer Sequences, again with Academic Press, and that had 5,000 sequences in it. And then I waited a year. Then sequences really started to pour in, because by then we had electronic mail, and it was a lot easier to communicate. Email made a huge difference. So in 1996, I put the whole thing on the web. I waited until I'd accumulated 10,000 sequences, until it had doubled, and then I just put it on the web, and I called it the Online Encyclopedia of Integer Sequences, the OEIS, as it's come to be called. In fact, we called it that right away. And so today, in its present existence, it's up to 200,000 sequences. So it's grown. It would be impossible now to publish this as a book. It would take a bookcase the size of this wall to accommodate all the sequences.
Now, I mean, there's an infinite number of possible sequences, but I mean, as you said, you only have, a couple 100,000, which is still an amazing amount of integer sequences. So how do you determine which sequences are actually like, if you look at a sequence, how do you kind of get a feeling whether or not a sequence is actually interesting, or it's just someone tossed a bunch of numbers in a list and said, hey, look, I have a sequence?
This is a problem, of course, because people do tend to sometimes send in silly sequences they've thought up with no particular merit to them. Well, we have certain standards, of course. We don't accept any old junk. But if the sequence has some, first of all, it has to be well defined. It must have a precise definition.
Okay.
And that's one of the first things an editor will do, is look at the sequence and say, does this make sense? Is the definition precise? It's a sequence of numbers, the nth number, does it have a good definition? Is it a definition that other people might be interested in? If it's really specialized, you might say, well, the typical sequence we don't like to get are things which have, for instance, based on numbers that have 666 in them, because some people think that's lucky or maybe unlucky, the number of the beast. So you could say, all right, let's look at the prime numbers that have the digit 666 in them. Well, that's a kind of sequence that is marginal. It's perhaps interesting to some people, and maybe we should include it, because there are a lot of people, a lot of superstitious people, and so this is a sequence that might come up, and so maybe we should include it. On the other hand, if it's really far-fetched, then we would reject it. Of course, we don't accept things like phone numbers, social security numbers, short finite personal sequences. They definitely don't belong. This is a scientific database. My criterion is that basically sequences should be well defined and they should be interesting to more than one person. On the other hand, there are certain finite sequences that come up often enough. For instance, the numbers around a roulette wheel. This is a sequence that sometimes comes up on tests, so that's in there. One of the things I've always tried to do is include sequences that come up on IQ tests, just because that's one of the functions of the OAIS, to help people pass these tests.
So, I mean, you've had a lot of good reactions, clearly, from people who are very excited to use this and who've apparently used it for a lot of various...
Wherever I go, people come up to me and say, boy, thank you for the OAIS. It saved me months of work.
Have you ever had anyone come up with a negative reaction to you, other than you didn't... I assume you get some people like, how come you didn't accept my sequence? I'm sure that's happened, but have you ever had someone who actually came up like, I wish you hadn't have done that?
There have been some cases. There was someone, I took a couple of sequences from someone who makes his living measuring people's IQ. And one of the things he would do is give them a test, give them a set of sequences to see if they could guess the next term. This was one of the things he did, and then he would charge them a certain amount of money and tell them, okay, your IQ is such and such. And so I took a couple of sequences from one of his tests, and he wrote to me and he said, I really wish you hadn't done that. But on the other hand, some of his sequences were taken from the OAIS because I recognized them. They were classic puzzles that I had in the OAIS. So that was one example. There have been also, we've had some problems with, I certainly don't want to mention any names, but people who exaggerated the importance of their friend's work. And so they would submit sequences. The sequences themselves were not uninteresting, but the comments that went with them were sometimes unacceptable, by saying this sequence was invented by so-and-so, and when this was a sequence which was certainly not invented by this person. That's always a difficult question.
So, say someone, because you accept sequences. I mean, as you say, you just have to register, and then if you have a good sequence, you can submit it. Say someone wanted to get their name on a sequence, and how would they go about in the beginning parts of figuring out a sequence that might be interesting, and how would they start with the generation of it? Like, how do you create a new integer sequence?
This is actually something I generally discourage people from doing. We don't really want people to go around making up sequences, especially so they get included in the OEIS.
Okay, so-
I'm really more interested in sequences that originated in their work, in some working on some mathematical question, for example, or some counting problem, in statistics, perhaps, some sequence that has an existence independent of the OEIS.
Okay.
And once you have the sequence, then you go to the web page for submitting a sequence. It will ask you to type in the terms of the sequence and give a description and so on, and type in what you know about it. And then at the end of the page, there's a submit button. Yeah, we don't really like people who say, all right, I'll try to think of a sequence that's not in the OEIS and send it in. That's really not what we like.
Fair, absolutely fair enough. I think that's probably about it. I mean,
Great.
Thank you so much. It's been fantastic.
Good. All right. Well, it's easy to log on and see.
Oh, yeah.
If you register yourself, you can play around with it.
Let's close off this part of the show with some audio from the online Encyclopedia of Integer Sequences. In particular, let's hear what the first couple hundred entries of Rackamon's sequence would sound like if it was played on a grand piano. Until now, we've been talking about the numbers that everyone thinks of when they hear the word. Specifically, we've been talking about integers. But integers are not all of the numbers. Actually, integers make up precisely none of all of the numbers, but that's for a different day. There are also the real numbers, or decimal numbers to give them their more descriptive name. And while they're not as simple as the integers, they can be just as interesting. Don't believe me? How about we ask the man who has created a 700-page catalog of them?
My name is Michael Seamus. That's S-H-A-M-O-S. Right now, I'm a professor in the School of Computer Science at Carnegie Mellon University. I had previously taught in the mathematics department and in the statistics department at CMU. I've been there since 1975, but I took a very long leave as an adjunct faculty member to start a couple of software companies and to also be a full-time intellectual property attorney. But I came back to CMU in 1998 and have been there full-time since then.
So the main reason I'm here to speak with you is to talk about the catalog of real numbers. Now, I'm not entirely sure exactly why you've done this, because I was looking through it, and it's quite clear to me that it contains precisely 0% of all of the real numbers.
Yes, of course. Yes, any discussion of the real numbers would have precisely 0% of them. That doesn't mean that it's uninteresting, however.
No, that is very true. I've spent
Yes.
quite a few hours actually just flipping through it for no real reason.
Remember, events of probability 0 occur all the time. And they may be interesting to talk about just because they are of probability 0. You're quite correct. One could never list all the integers even though they're denumerable. It would be completely hopeless to even dream about listing all the real numbers, but that was not the intention.
Oh, phew, I was really worried about precisely why you were doing this in the beginning. I'm like, he's just clearly skipping ones in here.
Yes.
I mean, there's a lot here that aren't listed just in your
but they're
basic
not,
ones.
But those aren't interesting. The ones that are skipped.
Yeah, I mean, you skipped a bunch of integers.
Yes, not all integers are interesting. I didn't do it to do it. It was a byproduct of a different research effort.
Okay.
And I started collecting it, but to tell you why that is, we have to go back a long time.
Take me on a trip.
Yeah, and so it starts when I was an undergraduate. I went to Princeton, and I wanted to major in physics, and I did major in physics, but there you couldn't declare a major in physics until junior year. And in sophomore year, I wanted to do something concentrated. The math department was available. You could concentrate in mathematics starting in sophomore year. So I did that. And I got exposed to a lot of interesting folks at Princeton. There were topologists there. There were game theory people there, knot theory, analysts, everything. And I took a couple of very interesting courses. One was a seminar called The Topology of the Real Line. And in that course, we had no particular textbook. But at that time, I was taking differential equations and a number of other math courses. And I developed a lifelong, dichotomous love-hate relationship with math textbooks. The problem for me with math textbooks is that they proceed very logically. You start out with definitions, then there are some hypotheses, postulates, axioms, then you apply rules of inference, and you develop theorems, which you then prove. And the skill of learning undergraduate mathematics is learning proof techniques. It is not learning mathematical discovery techniques. They don't teach you how to find new theorems. They teach you how to prove things. And I couldn't escape wondering who dreamed up these theorems in the first place. There are some theorems that are so non-obvious. Forget about whether it's easy or difficult to prove them. How would you even conjecture them? How would you even dream that they were true? And it all came to a head for me in complex analysis. This was a 2-semester course, a full-year course. It was taught by Gerard Waschnitzer. Waschnitzer was famous then. He's not a really big name in analysis. But he had this amazing habit of not being confined by the blackboard. If he was writing out a proof and he got to the end of the blackboard, he would simply continue writing with chalk on the walls in order to complete the theorem. At the end of the first semester, when the bell rang, he had to stop because the semester was over. But then at the beginning of the next semester, he started off exactly where he had left off from the previous class, as if there had been no interruption. So I was exposed to lots of characters like this. But the theorem that got me for years, and I'm still wondering about it, is something called the Hadamard three-circles theorem. This is a theorem in complex analysis, which I could give you the statement of it, but it's sort of beside the point. It's the kind of theorem which, once stated, is not difficult to prove, but you could never in a lifetime come up with a statement of the Hadamard three-circles theorem. And for decades, I wondered, how did they do it? How did Hadamard do it? Well, when I got to CMU, turns out that we have a fairly extensive mathematics library. There's a lot of historical material. And I was able to look up the correspondence, the letters that Hadamard had with his contemporaries. And I could see, over a period of months, in the exchange of letters, how the statement of the theorem evolved. And what I realized was they weren't teaching anything like that in any mathematics courses. What they would do is show you the theorem and say, now prove it. Oh, you don't know how? Here's a proof. And I became much more interested in the mathematical discovery aspect of things than in the proof aspect. I was never a champion at complex analysis, so I wasn't going to work in that field. But I was always very interested in discrete math. I had been familiar with Sloan's Handbook of Integer Sequences for many years. It had been extremely useful to me in my own research. I used it for exactly the purpose for which it was intended, which is you're doing experimental work, you come up with a sequence of integers. You don't know what the underlying law or rule or formula is for them, and so you look them up in Sloan's book. And of course, once you know that, it gives you a prediction of what the next number in the sequence ought to be. So you can then do your next experiment and verify it. And you say, aha, now I'm probably onto something. Let me see if I can go prove that. So at that point, the mathematical discovery part is over, and then it becomes a sluggish process of proving the truth of what you had only up to then conjectured. So I was very familiar with Sloan, loved it. The problem that I chose to work on, a maddening problem, still maddening, and I to this day don't understand why we haven't solved it, had to do with Riemann's zeta function. Now, I believe I'm the only mathematically trained person on Earth who's interested in the zeta function but is not interested in proving the Riemann conjecture, which appears to be the only reason that other people study the zeta function. Okay, I have no interest in trying to. By the way, if somebody resolves the Riemann conjecture, I'd be interested in knowing what the resolution is.
Yeah.
But I personally have no interest in participating in the research or the proof. No, I was fascinated by Euler's formula for the closed form of the zeta function at where the argument is an even integer. So zeta of 2 is known, zeta of 4, zeta of 6, zeta of 8. All of those are rational multiples of an integer power of pi. But zeta 3, 5, 7, 9 are completely unknown. There are no closed form formulas for them. In fact, for the longest time, it wasn't even known whether they were irrational until Apéry produced a proof that zeta of 3 was irrational. But that shed no light on whether there even exists a formula for zeta of 3 in terms of other known constants. No one's proven or disproven that. And so while I was worrying about all this, Mathematica came out. I was an early adopter of Mathematica. It seems to me in the early 90s I was using it. I was an intellectual property attorney at the time. They had just bought me a Mac, which I remember at the time cost $10,000. It was a Mac with a printer and a screen which would be regarded as tiny by present standards. And one of the pieces of software available for it was Mathematica. So I got Mathematica, and I started playing with it, and I noticed that it was fantastically good at closed form summations, infinite sums. So you could type in an infinite sum in symbolic form, and if it would munge over it, and it might produce a closed form. And so I said, aha, now there are all kinds of things I can do, because I know all kinds of things that are related to zeta of 3. Let me see if any of them magically pop out with a closed form. Maybe we know the answer without knowing that we know the answer. So I started typing in all kinds of formulas related to zeta of 3, getting closed forms for some of them. And I started having a problem, which was I didn't know whether I had seen one of these before. So I needed to index them in some way. And when you have a closed form expression, you could just numerically evaluate it. And so I started collecting these formulas not by their symbolic form, of which there are many transformations, but by their numerical value, for which there's no transformation. And I collected hundreds of these, and I wasn't finding any formulas for zeta of 3, but I was finding all kinds of other interesting things. And what I would do is I noticed that I type in a formula, get a value, put it in my little index. Then 2 months later, type in a different formula, get a different closed form, but it evaluated to the same thing as a previous value. Now, of course, I was keeping a precision of 20 digits. So, of course, as we all know, the fact that two numbers share the first 20 digits of their decimal expansion means nothing about whether they might be equal or not. But at least it raises a fair conjecture that they are, which then is subject to proof by other means. So what I found was this little book that I was collecting, purely for the purpose of doing research in the zeta function, was ending up allowing me to make many, many conjectures, some of which were of a trivial nature, but some of which I found that I thought were profound. And the index began to be a mathematical discovery tool, at least for the discovery of conjectures, if not for the discovery of proof, which is not what it was intended for. Well, it took on a life of its own then, because I found that it was much more fruitful to conjecture things which had some hope of being proven than to simply hunt around for a formula for zeta of 3, sort of like stumbling around in the woods in the dark. And because I'm a goal-oriented person, I liked results rather than negative activity. And so I started writing code. As this list grew, I wrote code to hunt around for possible relationships. I wanted to see, for triviality, are any pair of numbers in there, when summed, do they give a third number that I already have? The product, the sign of one number, is that in there? A to the b, if A and B are in there, is A to the B in there? And if so, might there be a non-trivial relationship between the formula for A to the B and the separate formulas for A and B? And it turned out in many cases that was true, that the symbolic expression for A, and the symbolic expression for B, and the symbolic expression for A to the B had nothing to do with one another. The symbolic expression might be an integral, for example, whereas the two A and B separately might be something that didn't involve integrals. And patterns began to emerge, and I started off proving things that were conjectured by their mere appearance in the list. Well, I said, well, this is the generator of PhD theses. I already had a PhD, so I didn't need one. But I thought this might be a great source for math graduate students who are always looking around for a thesis topic. And so I started collecting formulas and putting them in the index that had nothing to do with the zeta function. I went to Gradstein and Rijik, which is a thick table of integrals and products. And I started evaluating the closed forms in there through Mathematica, and then sticking them and their symbolic expressions into the catalog. And what emerged was, and you say you looked at it, so you know that an entry will show typically some simple closed form, like 2 pi cubed over 3. Then there'll be some equivalent summation forms. Then there'll be some product forms. Then there'll be some integral forms. Then there'll be some possibly odd values of the gamma function, or strange values of other special functions. And it sort of took on a life of its own. I worked on it for 15 years in my spare time. It wasn't a chore. I loved doing it. And it got bigger and bigger and bigger, and more interesting things started to emerge from it, and I wrote more code to discover more things. And it's led to research papers which I've produced, and I've given some talks on it. And finally one day I just decided to make a PDF of it and put it up on the net and inform a few people like Neil Sloan and Simon Plouffe. And it's sort of taken on a life of its own since then.
Now, one other thing that you mentioned in your intro is you kind of invoke the famous Ramanujan Hardy story
Yes.
of the
Interestingness of numbers.
Yeah, interestingness of numbers, and Hardy saying that the integers were Ramanujan's personal friends.
Yes.
And you specifically say you want to make the real numbers people's personal friends.
Yes.
So I was wondering if
Well, there are more of them.
Yeah, well, there are more of them. Every single person can have an infinite number of unique ones. Of course, that would also technically be true of integers, but we don't need to get into that. Right. But I was wondering if you could just maybe tell me what you mean. What would it mean for me to have a real number as a personal friend?
Oh well, I'll tell you because I have one.
Okay.
Zeta of 3 is my personal friend. I know hundreds of relations, hundreds of equations that are equal to zeta of 3. I'm constantly looking around for things in the mathematical world that might relate to zeta of 3. Zeta of 3 is my passion, because I've often mused that how is it possible that we know enough math and science to get man to the moon, but we cannot find a closed form expression for zeta of 3, or prove that no such closed form exists? How is that possible? Well, it's because President Kennedy didn't make it a priority for us to find a closed form for zeta of 3. If we'd poured billions of dollars into that, maybe we would have gotten farther with it. But I would agree with the the attitude that probably getting to the moon was a more important goal. Nonetheless, that's my friend. And other people, there are some people for whom the golden ratio is their friend, and other people love E. And some people even love imaginary numbers like I.
And now, it's finally time for us to join the author Alex Bellos for a discussion all about favorite numbers.
The favorite number experiment, is that the word
That
you
was
went for?
survey, maybe.
Favorite number survey. I'm sitting here with Alex Bellos, who did the favorite number survey. What is it? I mean, what specifically were you asking people? I guess it's kind of inherent in the name, isn't it?
Right, well, what I wanted to find out was, first, what's Britain's favourite number? And then I realised, why limit myself to this small island off the coast of Europe? Why not find the world's favourite number? And this is something that you can do easier than you ever could before because of the internet. So I have a website, favoritenumber.net, and on it, so as not to be suggestive anyway, it just says, what is your favourite number? And then it says why, and you can fill in those. So either with letters, so you could write out if it's 3, THREE, or the digit 3, and why. You can write whatever you want. And then at the bottom is, I don't have a favourite number. So you can also say, I don't have a favourite number. When you click on that, it goes through to another page which says, hey, 1 minute, please, can you answer these extra questions, which will help me work out if there are any interesting trends. And it is, what's your nationality? Where are you? So location, gender, are you a man or a woman? How old are you? And then the level of mathematical ability. And I say either up to 16, up to 18, or university educated. And since I started this survey in the beginning of the summer, I think it was in June, I have had, and I can tell you exactly, 34,671 entrants from all over the world, from probably most of the countries in the world, definitely well over half. People of all ages and all genders and mathematical abilities. And it really has been sort of phenomenal to me how this seems to have struck a chord, that people really seem to be interested in this kind of thing. And when you think, well, surely you're interested in it, that's the thing. I was not interested in it. The reason that I got interested in this is that after having written a book on maths, I would go and give talks. I would sort of meet people, and they'd be like, hey, you the math guy? And I'm like, yeah. And he goes, hey, so what's your favorite number? And I thought that was like a heckle, an annoying heckle. People just trying to sort of tease me or demean me. And I was thinking, no, favorite numbers, that's ridiculous. It detracts from the seriousness of the maths, which is what I'm here to talk about. But so many people asked me, and when I started to ask around, even some of my friends, I'm like, well, do you have a favorite number? They're like, oh yeah, it's 13. Oh yeah, I always loved 8. I thought, this is weird. So like people do have favorite numbers, because I myself don't have a favorite number. I think that's kind of crazy. But the more I asked, not only did I realize that most people who I asked seemed to have a favorite number, no one thought it was a ridiculous question. And they seemed to have their beliefs that they loved these numbers, that they were favorite, really quite strongly. So I then decided to do this survey. And like a kind of non-smoker, like a smoker who then has become a rabid anti-smoker, I've been someone who's not really liked favourite numbers to someone who's kind of obsessional about them, because they tell us so much about lots of different things. Obviously, I'm learning quite interesting new maths. People say numbers that have these properties that I didn't know, but also how we as humans relate to numbers. kind of make them personal. We invent these emotional responses as a way of kind of accepting them within our worldview. So someone who is like afraid of numbers might have a favorite number because it means that they become less scared of numbers. Someone who is mathematically minded might have a favorite number because there's some aspect of that number that reflects with their own personality. And I'm going to try to quantify all the different reasons that people give and see if there's any trends through age, gender, mathematical ability, and nationality. And also I can look at the answers and code them. So the most common answer of what your favorite number is your birthday. I was, 3 is my favorite number because I was born on the 3rd. But there are lots of numbers that are coming out that are never ever mentioned when the reason is it's my birthday. I'm not sure, but I think 28 or 30 or something. So of these 34,500 people, several thousand have said, I like this number because it's my birthday, but none of them, I think, have said, I've been born on Thursday. I'm born on, say, the 30th or the 28th. I can't remember what it was. So that's sort of interesting to me. Why are certain numbers more appealing for choosing as your birthday than others? And also, I haven't collated the full reasons yet, but essentially, odd numbers occupy more of the top numbers than even numbers do, and prime numbers within those odd numbers even more. Now, sort of why is that? Is that purely cultural, or is it something about the mathematical nature, something about a number's primeness or oddness that makes us cherish them more? These are just the paths that this research into favourite numbers is taking me down, which, to me is sort of endlessly fascinating. There's something very something very basic about numbers and our relationship to them, which is interesting, and I think interesting to people who are mathematical, but also to people who are, say, I don't like maths. Oh yeah, favourite number is 4, obvious, for example. And it's interesting, I can see here, this is the database that numbers are coming in. And so the last number that came in was a 22-year-old female from China who has university level maths. Her favourite number is 6. It sounds like sexy. Okay. lots of people say 69 FNAF, but not that many. And then so here we have a 27-year-old male from the United States who says this is a classic answer. 7 is his favourite number because 7 seems to pop up a lot in my life. Also, my birthday is on the 27th, so perhaps it's something to do with that. Now, lots of people who choose a number give the reason by saying it appears a lot in their lives. But every small number is going to appear just the same in someone's life. I do not believe that really one number will crop up more. What it is that you notice that one more because you're already primed. It's like kind of confirmation bias or whatever we want to say. But the idea that we have these things, that incredibly powerful psychological sort of default reactions to seeing numbers, is that it's a way of controlling the chaos of the world. If we think that one number is our number that's following us about, it's a way that we can kind of grab hold of something. So that in itself is interesting, that the way that numbers are our way to kind of make sense of the world in a very, very sort of basic sense. Even to, this is a maths person who's got a maths degree. So getting better at maths and more sophisticated at maths doesn't mean that you lose that very basic idea that a number is following you around. You'd have thought someone who's got a degree in maths isn't going to think something as so self-evidently bogus that one number happens more in their lives than any other number. This is one of my favourite ones. It's from a woman in Canada who's 34 with university level maths. Her favourite number is 7.07 because that number is 10 over root 2. And her reason is, I had been doing a lot of trig homework for a calculus class I was taking in undergrad, and this number appears a lot. At the time, I was sort of weirded out by the fact that I kept waking up at 7:07 instead of 7:30 when my alarm was set for. Anyway, one Saturday, I went to my local art supply store and bought some paintbrushes. To my surprise, the total came to $7.07, and I sort of blurted out, "Oh, that's 10 over root 2 again," to the very cute cashier for whom I had a rather pathetic crush and who I was constantly embarrassing myself in front of. After explaining myself, he was duly impressed and began embarrassing himself in front of me whenever I came to the store. And from that point on, I realised there's a brand of arty guys that like nerdy girls, and this still makes me happy, some 15 years later. Now, how brilliant is that? You know, it's a story, it's some important moment in her life, which is symbolised by a number. You know, that's the richness that you're getting by the qualitative answers to this survey. So, you know, 37, it looks mysterious, like a cloaked villain from a silent movie. A 19-year-old, she must be at university doing something to do with maths in America. 64, and one of the reasons is, it sounds epic. Say it. 64! Someone likes 23, because 23 factorial is the first factorial to contain all the digits from 0 to 9. And both the digits of 23 are the first two primes, and 23 is the number of base pairs in the human genome. I've got 34,500 of these. I mean, it's kind of amazing. And when I come to look at them more closely, I'm slightly daunted by the idea of going through it. I'm going to find some really fun things. Also, there are quite a lot of synesthetic answers with people, say, linked to colours. So this is from a 27-year-old woman from India. Favourite number 9, because it's purple and it's my birth date. It's also odd, which I like better than even, because I think odds are way cooler. Plus, I relate it with 3, which is a prime. Primes are the coolest. 27, because I also love 9 and 3. And what do they divide into? 27. I do that sum all the time. Something like 3,435. Because 3435 is equal to 3 to the 3 plus 4 to the 4 plus 3 to the 3 plus 5 to the 5. In other words, it's the sum of each of its digits raised to the power of themselves. And that's the only number for which it's true in base 10. Yeah, put that in your pipe and smoke it.
Do you have a favorite number?
Oh, got it. Then the favourite number. Oh no! Oh dear! Oh.
Do you have a favorite number?
Do I have a favorite number? I wish I had to think. I mean, there's just so many.
Do you happen to have a favorite number?
Favorite number? Yes. Do I know the number?
Yeah, when I'm asked that question on occasion, I guess I would say 7.
No, I do not have a favorite number.
I suppose I'm supposed to say E or pi here or something. I'm gonna say 7. I like 7 a lot. I wouldn't say I'm like super religious. It's part of my background though, and I love the historical and religious implications of the number 7.
I like 12758. 12758 is the first number that's not the sum of distinct perfect cubes.
144. It's perfect square, so that's nice. I think why I like it is because I think growing up learning multiplication tables, 144 was always the limit. So it was always like that was the last thing down there in the bottom corner. And there was, I think the multiplication table is beautiful to begin with. You know, all the symmetry, and there are all sorts of things you can explore there. But Yeah, something about that number just kind of feels like done.
Do you have a favorite number?
Favorite number? 2, maybe?
Do you have a reason why it would be 2?
Well, many reasons, right? So, but one of the reasons is that the value of the exponent of power law degree distribution in many networks is actually equal to 2, not equal, but is very close to 2. And in our recent work that we probably don't have time to discuss, we found that the same value of power law degree distribution applies to the distribution of degrees of the nodes in the causal network of the whole universe.
37, and that's something sort of personal. When I was dating my wife, I told her that I would stay with her for 37 years. I don't know where that number came from, and it's sort of been a joke for a while. We're currently coming up on about 32 years, so I've got at least 5 years left. At that point, I'm allowed to reconsider.
I guess I would say 60. And the reason why is that it's the, if you know group theory, it's the smallest non-abelian finite simple group, non-trivial one.
17. Well, I have 2, I guess. 17 is one of them, and 1 plus the square root of 2 is the other. Well, 17 is just a number I chose, I guess. I've always liked it. It's irrational. 1 plus the square root of 2 is a fantastic proportion. It's also known as the silver ratio. So it's sort of the neglected brother of the overrated golden ratio.
I do feel the need to point out 17 is not irrational. 1 plus the
It's
square root of
irrational
2
that I
is
like
irrational.
17. 9, because my birthday is 9/29/49. Okay, and so that it seemed like somebody was trying to give me a message there. So it's a nice arithmetic progression with a lot of 9s in it.
A favorite number? No, I don't.
Okay.
I have a favorite sequence.
Oh,
which
what's
is
your favorite
Reckermann's.
sequence?
Reckermann's sequence, A5132. It's my favorite sequence because we don't know how it behaves. Reckermann's sequence has a very simple definition, and yet, in a way, it's the most complicated sequence in the database because we don't know what happens in the limit. We've computed something like 10 to the 74 terms of the sequence, which is really rather a lot. And we still don't know what's happening.
Do you have a favorite number?
I don't actually.
7.
7. Do you have a reason behind 7, or is it just...
No, I've always liked the number 7.
Okay.
Yeah, it's a prime number. Most people pick primes, and I don't know. Yeah.
Let's say 5. That was on my softball jersey, so it's a nice round number. Let's go with 5.
The 29 is a prime, and it's a very interesting prime from a number theory point of view. So it has certain properties that have played a role in my life over time, and so I've always viewed 29 as my favorite number.
I'm friends with Zeta 3 because I've spent so much time with him. But favorite implies a love. I can't say I'm in love with Zeta 3 because I find him impenetrable. There's information I want to get out of him that he won't tell me. Whereas a friend wouldn't hold back. And so I wouldn't say that there's any particular number that's my best friend. I'm friendly with lots of them. Pi has revealed a tremendous amount about itself, as has E. I do indeed like those. There are others that I'm estranged from. A gamma of a half, for example, it's not a particular friend of mine.
I like the number 2, and I like the number 10. 10 is a number that I think, one, is a part of my birthday. my birth date, and also very representative of the 10 fingers we have, 10 toes. It's just a nice tidy number. And then 2 I also like because it's symbolic. I think that I have twins, and I'm Gemini. I like 2.
I'm going to say I. We're like complex numbers, aren't we? Yeah, good. I love I because it was someone telling me about that when I was at school. I was doing some extra maths, and they brought in some extra teachers, and he just started telling us about complex numbers when I was about 14, I suppose 15, and I thought this was the coolest thing. Oh my goodness, I'm getting almost tearful about it. It was, I've never ever talked about this before in 43 years or something like that. It made me realise that this was not only intellectually satisfying, but really exciting, and it absolutely determined that I was going to try to do maths. And so I went to do maths. And I really enjoyed complex analysis when I was at university. I only used it once in my work since, sadly, but I did use it once in the past. And I absolutely love to do this. It had that sort of mind-bending, mind-expanding, ludicrous nature, and yet done absolutely straight and rigorously, that has kept me really enjoying mathematical ideas since then.
It is silly in lots of ways, but lots of things in life are silly. Yeah. And it is strange. I'm not sure you can make a moral judgment about whether it's right or wrong to have a favourite number. It's just the case that lots of people do. And when you ask that question, I wasn't inundated with people sending me emails saying this is ridiculous, or with people clicking the box, I don't have a favourite number. Overwhelmingly, people embraced it. Like, oh my God, this is fascinating. I really want to know. People take this stuff seriously.
I know.
I'm Jay Frosting, one of the producers of Relatively Prime. And that's all for Relatively Prime this time. We want to thank the guests Alex Bellos, author of Here's Looking at Euclid, or Alex's Adventures in Numberland if you're in the UK, Tanya Kovanova, whose wonderful website is numbergossip.com, Neil Sloan, creator of the online Encyclopedia of Integer Sequences, available at oeis.org, Michael Shamos, compiler of the Catalog of Real Numbers and the Favorite Number Gang, and the musicians Soap and Foam, Joe Nathan 007, and Jared Korak, without all of whom this would not have been possible. Please go to Rel Prime for a list of all the people who contributed. If you want to find out more about the guests, or the music, or if you want to discuss the show, please join us over at relprime.com. And while you're on the internet, why not head over to iTunes and leave a review of the show? It really does help other people find it. After that, search for Pre-Recorded Late Night, my comedy show where we parody American culture with absurd interviews. And if you have any feedback about Rel Prime, just email Samuel at acmescience.com. That's his real personal email address. Relatively Prime is licensed under a Creative Commons Attribution Share-alike license, and any remixes are greatly looked forward to. Thank you for listening, and we hope you come back for the next episode.